In this video, I will be discussing the motion of an object dropped from rest that is noticeably impacted by drag. I will first introduce the principles involved with my observations, then the methodology for both the initial experimental model and the computational models. I will compare these models, report my results, and conclude with the implications of said results. The major purpose of this lab is to model Newton's second law and observe the interactions of different forces on a falling object. The three fundamental principles relevant to this experiment are Newton's second law, also known as the momentum principle, the force of gravity, and the force of drag. The momentum principle describes the motion of an object based on its change in position impacted by the force acting on it. We quantify this motion as the total force acting on an object equaling its change in momentum or change in velocity times its mass divided by the duration of time observed. One component of this net force is gravity. Gravity is the force between an object of mass A and the Earth, which can be summarized by the constant 9.8 meters per second squared times the mass of object A. In this experiment, another component force, drag, opposes the motion of an object due to collisions with the moving object and the molecules in the fluid that it is moving through. In this case, that is air. The opposition is quantified as a force proportional to the square of the speed of an object, multiplied by an experimentally determined constant. For the observational model, I dropped a crumpled piece of printer paper from the top of my door frame with a height of 2.93 meters. The room had negligible airflow that would impact the motion, which is why I chose it for the surroundings. I chose a piece of paper as a system because of its light mass and observed fall time being slower than a heavier object I had available. After recording the video, I analyzed it using the chalkboard application, where I calibrated the motion to the fixed door frame's height and set my axes with the origin placed at the start of the motion where t equals 0. I then tilted the axis leftwards to accommodate the observed motion's trajectory being roughly at the same angle. First computational model was created under the assumption that there is no drag force and the only force acting on the system is gravity. In this model, acceleration is constant as shown by the velocity graph with the constant slopes. To make this model, the initial position and velocity were set to 0, as well as the variable b, the drag force constants. The net force variable was defined by the system's mass multiplied by the acceleration due to gravity constant 9.8, multiplied by the direction of motion, which was the vector j hat. In this case, the weight force is negative due to the position of the origin and the subsequent direction of motion. This force was constant and used to create the graph and the position and velocity update formulas contained in a while loop that ran the code from time 0 to time 0.8, with the time increasing by 0.011 seconds each iteration. As we will soon discuss in more detail, the final graph created by this model differs from the observed motions model. This is because it does not account for any other force present in the motion. Without the inclusion of any opposing forces to gravity, the predicted final position of the system is lower, indicating that the object falls faster than it actually does. To improve the previous model, a secondary force was introduced to the simulated system, drag. To do this, the same initial conditions were used, but the net force variable changed. A new force variable was included to simulate the constant opposing force of motion represented by the drag equation. The drag force constant B was chosen experimentally, where I ran the code multiple times, adjusting this value until the final position of the object was roughly the same as the final position of the object in the observational model. The drag force equation was given by the magnitude of the velocity squared multiplied by the direction vector j hat. With this equation, the net force was then updated to equal the drag force plus the weight force, resulting in a model that much more closely resembled the observational model. When comparing the three models, we find that the computational model that includes drag produces a more accurate description of the motion captured in real life. Though there is some deviation in the improved model, this can be attributed to forces in the surroundings not considered in this lab, and to improve it, a more controlled environment could be used. The results of this lab show that when considering models that do not have a strong enough weight force to overcome the effects of opposing forces, to better understand this motion, we must consider these forces and include them in our calculations. These models better explain the relationship between moving objects and force and point out the importance of magnitudes when describing motion. The computational model without drag predicts a terminal or constant velocity, indicating a net force of 0. In a case where the object was thrown down, the case would be different and more likely to be terminal because drag force is proportional to speed, while gravity is not, meaning that the drag force would be stronger and more likely to balance out gravity, nearing a net force of zero.